breaking wave is a primary agent that changes the shoreline of our coast. Energy which is traveled across the ocean is released as each wave crashes onto the land. Storms which create waves form, move, and die out far at sea, causing waves which come to our coast from different directions at different times. The tide flows in and out, constantly changing the water level, and each crashing breaker changes the shape of the bottom. So each wave arriving at the beach is different, and the beach it arrives at is different because it was changed by the preceding wave. The sand of the beach is in almost continuous motion. If you watch the waves breaking on a sandy beach, like this one, you can see a wave break and the water run or swash up the beach. As it slows down, some sinks in, and the rest flows back toward the sea as backwash. Both the run-up and backswash carry a thin film of sand suspended in the water. So this is the first question we must answer if we are to understand the beach. Is sand being added to or taken away from the beach? One wave moves very little sand, and the effect of even 100 waves would be hard to measure. But if you could study this beach for a week, a month, or even a year, you could learn some very interesting things. The beach is always in motion. But within the constantly changing beach, some features would be easy to find. Just off the beach, the breaking waves create an offshore bar or ridge of sand running parallel to the beach. The trough between the bar and the beach varies in depth and directs the water from the breakers along the beach until it reaches a break in the bar where it runs back out to sea. At the break in the bar, the returning water often forms a rip current, which occasionally sweeps swimmers out to sea. If you're unfortunate enough to get caught in such a rip current, the best solution is to swim out of the current by swimming along the beach. If you try to swim against the current, it will simply sweep you out to sea. But if you exercise some care in selecting a swimming site, you should never encounter a rip current. The sandy foreshore on which the waves crash slopes upward to a low ridge called the berm. The berm marks the highest point reached by the wave. From here, the beach slopes gently down, forming the back beach, which stretches from the berm to the dunes. The dunes mark the line that separates land from beach. During the summer months, generally smaller waves bring sand to the beach. The berm is gradually built out from the dune line, increasing the width of the beach. But in the winter, storms bring larger waves which erode the beach, carrying away the sand. The result is a narrower beach, but because the waves are larger, the berm tends to be higher. There are smaller features which you can observe every day if you walk along the beach. You can see wash marks which mark the end of a wave's travel up the beach. The thin film of sand deposited by each one marks the pattern of surf beat, or rising and falling tides. With a rising tide, each succeeding wash reaches farther up the beach, wiping out all the earlier wash marks. But when the tide ebbs, earlier washes are left on the beach. Part of the washing water that does not sink into the sand rushes back down the beach. Often, when the beach is reasonably steep, the moving water creates tiny crisscrossed valleys in the sand. There are many processes that we can see and understand on the beach. And why a flat sheet of moving water makes tiny diamond-shaped gullies is still a mystery. Water running out of small tidal basins on a relatively flat beach can flow fast enough to create uneven ripple marks. On the side from which the current is coming, they have long, gentle slopes. But on the lee side, they have short, steep ones. On the other hand, if a breeze stirs up the water in a tidal flat, the ripple marks that form are symmetrical, with equally sloping sides. One other larger feature that we don't understand are the beach cusps. You can see them as bays and horns that make the beach outline irregular rather than straight. They can range in size from 1 to several hundred meters from horn to horn. Scientists think they're related to wave size, but they don't really know why they form. The wind really dominates the beach. As it shifts, the waves that is formed at sea come as its agent to move and shift the sand. Waves seldom strike any beach head-on. Most of the time, they move onto the beach at an angle. So the sand they move not only moves on and off the beach, but also along the beach. This beach drift, as it is known, moves enormous quantities of sand down the beach, feeding sand into some areas and eroding it from others. It has been calculated that along the Outer Banks of the Carolinas and Virginia, more than 4 million cubic meters of sand may be moved past any point on the beach during a year's time. Yet such tremendous volumes are moved a few grains at a time, as wave after wave strikes the shore. As each wave runs up on the beach, the sand it picks up moves at an angle. When the water washes back down the beach, some sand is also carried down at an angle. So each succeeding wave carries the sand a little farther down the beach. Offshore, the water moved by the breaking waves also moves sand along the beach as a longshore current. So sand moves along the coastline, both on the beach and offshore. On the sandy shorelines like those which stretch from New Jersey to Florida, the reworked sand is formed into bars and spits, creating barrier islands. Sand is moved across river mouths and inlets, forming spits, hooks, and bars which shift and change unpredictably. These shifting mounds and islands of sand create trouble for man. Perhaps now you can guess why.